So this lab serves as our introduction to circular motion. Last week, or before exams, we talked about rotational motion, where we have a solid object that's rotating around an axis. So the whole thing is rotating, all parts of it the same angular velocity. And then we talked about the difference between angular and tangential and all that fun stuff, right? But here, we have a little bit of a different situation because we have a single object that is moving around some point in space. The point that it's rotating around is not necessarily part of that object. And we'll talk about how that happens a little bit more. But one big idea, the stopper in our lab, the thing that's moving in the circle, is it accelerating?
Yeah.
Yes.
Yes.
Turning.
It's always turning is an example of
acceleration.
Yes, because it's changing directions, right? Yes, right. Meaning there has to be a force acting on it. Forces cause acceleration. I guess I should say net force causes acceleration. What we'll see on Monday when we start looking at the notes and the concepts that go along with this is that the force that is causing this acceleration actually points towards the middle of whatever circle an object is, or this object is traveling around. So there is a force that points in this direction. In this lab, it's kind of obvious. Where does that force come from? Well, ultimately, yes, but the weight isn't touching the stopper. What is touching the stopper? The string. So the string is providing that force, but hopefully remember down in the, or way back when, right? Strings are tension forces. Newton's third law, strings work on both ends. So if this string is applying a force on the stopper this way, if we follow the string around and then it goes around the corner and then it comes down here, there's also another force that way. That's how tension works. Both sides of the strings pull with equal amounts. That's fine, but there's another force that's going on here, right? While the stopper was accelerating because it's going around the circle, was the hanging mass accelerating? It was just hanging there, meaning it was in equilibrium. What's true of an object in equilibrium?
There's no net force.
No net force, right? Forces have to balance. What's the force that's balancing out the red upward force of the string? Gravity is acting on this hanging mass, right? And so we have a weight force here balancing out that tension force there. Okay, good? So that's what's going on here. No net force on the hanging mass, it's just sitting there, but there is a net force acting on that stopper as it moves around in a circle because it is accelerating. Devin, go ahead.
Would the stopper be going like around 0.81 so it doesn't fall?
Not necessarily because, well, sorry. It's a good question, right? Because, hold on a second. It's a good question. Okay.
Did he stump you?
No, he didn't stump me. I'm just trying to figure out a way to explain it. So, Devin, and this is true of a lot of different situations, and I'll use this as an example. I drew that stopper in the picture, so string, stopper, like this. In real life, it can't be that way. It can't be horizontal because the string is pulling on it this way, but, sorry, that's a close-up of just the stopper. Does that make sense, everybody? Yeah, so, and then it's moving around like in a circle like that. Okay? It can't be horizontal because there's another force acting on this stopper. It has its own weight. If those were the only two forces, it would go in a circle because the red one is acting in the way to make it go in a circle, but it would also do what as it was going in a circle?
Go straight.
It would go down. So it would be like a downward spiral. But that doesn't happen because this string is not completely horizontal. Even when you were going really, really fast and it looked like it was just a plane, that's not what was happening. Somewhat exaggerated, but this is what was happening. When you're going slow, you can see this more, right? That the string actually tilts, kind of, so it looks kind of like a circus tent, I guess, if you want to think about it that way, right? So now the string is pulling this way, not horizontally.
So it's like the two.
And now we add, now what comes into play here?
Some of it.
So
Never some.
the components, right? So this red force now has a component that goes this way and a component that goes this way. This one causes it to go in a circle. This one balances out gravity so it doesn't fall down. It never could be completely horizontal, because if it was completely horizontal, we wouldn't have that vertical component and it wouldn't stay up. It would fall down as it was doing.
It goes up because
It has to balance gravity, because gravity pulls it down a little bit, right? But then if there's a component in the upward direction to balance gravity, now it won't fall anymore, right?
So
Now
is
it's in
that like-
equilibrium.
so is that like normal force, basically?
Kind of like normal force. It just doesn't come from a surface. It comes from the string. It's like here, okay? Meter stick, right? Is this meter stick horizontal?
Yes.
No.
No.
Because there's a gravitational force acting on it, right? So it's sagging, not as dramatically as this, but it is sagging. And if it's sagging, but it doesn't fall, what does there have to be?
Force pushing.
A- Something equal pushing upward to keep it from falling. Go ahead.
So is centrifugal force actually a force in the vertical direction?
No, centripetal force. So there's a difference between centripetal and centrifugal, and we'll talk about that a little bit more on Monday. Yeah, those are two different things. Yes. So
So one of them not actually.
one of them is not actually a real force. Evan took physics last year.
It's
So,
not like
yeah.
the,
so again, is this string completely horizontal?
No.
No, it's not. It never could be, because if it was, as I pull horizontally, there would be nothing to balance out gravity and it would fall down, right? Anytime we think of things that are horizontal, there has to be some sag to it to give you at least an upwards component to balance that gravity out.
Nice.
Now, could this be horizontal?
No.
Yeah.
Maybe.
No.
Yes.
Yes.
it is.
Actually, let me do this.
Oh, wait, yeah.
Yes.
Could that be horizontal?
Yeah, because
That could be horizontal, right?
Surface.
Because there's a surface to balance gravity out. We don't need an upwards component coming from my pole or whatever it might be, right? Here, right, with this, technically this couldn't be horizontal either because this is happening, right? Gravity pulls down here.
Couldn't, the table couldn't be horizontal.
True, the table
So
itself
the
can't be
whole thing,
horizontal
everything
either.
is like-
Yeah.
Is the earth sag, like the ground?
Well,
Because the center.
in that case, the Earth itself, you have like intermolecular forces that are kind of balancing out that gravitational pull. So that's kind of why the Earth is round. That's why big things are round, because gravity pulls them kind of from all sides and forms them into a sphere. So
The only way you can do that would be like a fully solid structure.
because then you have a fully solid structure would mean gravitational forces are pulling it inward, but then it's electrostatic, because like here, like if I do this, if I push my hands together, technically my hands aren't touching.
What? Oh, I got it.
So
It's
the
like a
What
sphere.
the pro-
do you mean your hands are tiny?
so
Like there's like stuff in the
I
middle.
watched
when
that.
we talk about contact forces, like like a normal force, this car is sitting on this table. Technically what it is, when we get down to like the atomic level, the electrons that are in
Yeah.
the atoms of the table and the electrons that are in the car repel each other, because negatives repel negatives. So technically they're not touching. Does that make sense?
What do you mean?
Mind.
What do you mean?
It's
But
just like a
now we're
slight hover,
Say again.
like a slight, like,
So they're
not
like-
even be able to see how.
They're one end of
Say again.
Like, is like, is so hovering, but you
So
can't
there
see
are
it.
Basically,
What?
you know,
Skateboard is a hoverboard.
Yeah.
in theory, I suppose, yes. So, but Anyway, so Devin, that's that question right
Wait,
there.
then how come it stays?
Say again?
How come it stays?
Because there's also protons in those atoms too.
Oh,
And so the protons kind of attract the electrons from the other object and vice
but
versa.
then they're basically still touching because the electron belongs to the carbon.
They set themselves up, like here, they've arranged themselves so that the negatives, the electrons and the electrons are like away from each other, but they're still like close enough to the protons. You know what I'm saying? It's kind of like, it's like at the beginning of the year, first day of school, right? You walk into a classroom and teacher says, okay, sit where you want. Okay. And the first day is kind of awkward, all right? But after the first couple days, you kind of like find your friends and you're like, oh, I don't like that person, so I don't want to sit by them. And you kind of get like all settled in. You know what I'm saying? That's sort of what's happening here at the atomic level. Those protons and electrons are all sort of like settling in to spaces where they're around people they like, but they're away from people they don't like, right? But then, right, at the end of the first grading period, what does the teacher say sometimes? I don't do this, but what does the teacher say? Change your seat, right? And now that's like me going, moving the car.
Yeah.
So, does that make sense? And then everybody has to rearrange themselves again and get settled in, right? And that's basically what's happening at the atomic level when we talk about, that's what friction is, that interplay between the protons and the electrons at that surface level of those objects and how they sort of rearrange themselves. That was not the.
So when the stuff is slippery,
when stuff is slippery or when stuff has friction, that's the electrons in your hand being repelled by the electrons in the surface, and they don't like to move across each other like that, right? Things that are less slippery, not that they have less electrons, but the way their electrons are held makes the interaction not quite as strong, right? Or say again. Kind of. That has to do more with how they arrange themselves within the substance itself. Okay, so it's kind of like how they're put together. So. All right, this is actually what I wanted to talk to you about. Okay? All right, so calculations. These columns you should have measured: hanging mass, number of rotation, time for rotations, and radius of rotation. Those are columns that you should have measured along the way. Okay. As far as calculations go, right? How do we calculate the weight of something? Hopefully we know by now.
Mass times gravity.
M times G, right? Okay. Make sure your M is in kilograms. Yes. Okay. All right. Time for one rotation.
10 divided by 10.
So
no, time divided by 10.
Time divided by the number of rotations, right? So the total time, we'll use capital letter T for the total time, divided by the number of rotations, where this is T and this is hashtag. Okay. All right. Hashtag rotations. All right. Next, distance for one rotation. We have a fancy name for that. We call that the what? It's the circumference, right? So distance for one rotation, you're just going to go 2 pi r. Make sure that you multiply it out. Don't leave it in terms of pi, right? And then tangential speed. This is one that I thought we needed to talk about a little bit. Tangential speed is how fast it's going around the edge, right? We talked about that in the last unit, okay? Any speed is meters over seconds, right? That's how we measure speed. So here we have the distance for one rotation. Here we have the time for one rotation. So if you know the distance of one rotation and you know the time for one rotation, you can figure out the speed of that rotation just by doing meters per second. Okay? Good there? All right. As far as your graphs go. Oh. Can I take a picture of that? Sure.
And I'll do that too. We did this. We just didn't do that. I don't know.
All right. Good there? All right. As far as your graphs go. So graph one says make a graph of tangential speed versus centripetal force. Centripetal force doesn't show up on your graph or doesn't show up on your lab anywhere. But going back to this picture, ultimately, where does the force acting on the stopper come from?
String.
String, but the string's attached to what?
The pen.
Well,
Well, the hanging.
the string's attached to the hanging mass. So ultimately, this force, the red force that's acting on the stopper, which we'll learn on Monday is called centripetal force, is equal to the weight. So when we make that first graph where it says centripetal force, you can change that to the weight of the hanging mass because that's what the centripetal force actually is. Okay, good there? And then radius and speed, and then mass of the stopper and speed. Okay, where it says put on x and y axis, when you go in Excel, x-axis always is in the first column, y-axis is in the second column when you put them up. Okay, you do need to put some trend lines. In each one, I added a power trend line. So we're just looking at relationships here. We're not actually putting in a line. We're actually putting in a, it's going to curve fit it as best it can. Please, 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 when you're making these graphs, make scatter graphs. Don't make line graphs. You're not connecting the dots. You're just putting cross plots on the axis. Okay, ready? We are in 134, which is the one just in this hallway right here. Ready? Go.
Yeah, remaining house.